Welcome. In the next series of videos, we're going to build up to the idea of binomial probabilities. But we're going to start with an easy example. We're going to just start with tossing a coin. All right. This is an easy example because when I toss a coin, it could be heads or tails. And if it's a fair coin, the textbook talks about a weighted coin, but if it's a fair coin, the probability is the same that it will land as either heads or tails. That's different than if we roll a die. This is what we'll be heading towards, where if I say, what is the probability, let's turn it to a 1. What is the probability of rolling a 1? Okay, it's 1 in 6. A not 1, it's kind of like the tails, would be a 5 in 6 probability. So we'll explore that more in a future video. That's a little bit more complicated. But I want to emphasize a big difference between the coin toss and a deck of cards, all right? So in the previous lessons, we had looked at conditional probabilities. So if I wanted to look at the chance of drawing 3 queens in a row, okay, the key is without replacing things in the deck and without reshuffling, okay? The first card I draw could be a queen, okay? It turned out this one's not, but there would be a 4, because there are 4 queens, in 52, because there are 52 cards in the deck, probability of this being a queen. But then when I go to draw the second card, it could be a queen, but there are only 51 cards left in the deck and there are only 3 queens. So there are 3 in 51 chances because the first card being played affects what happens for the second card. And then by the time I get to the third card, there are only 2 queens left in the deck. If I have succeeded in the first 2, there would only be 2 queens left as a possibility out of, I think we're down to 50 cards left. And there is a chance that I could actually draw 3 queens in a row. If I wanted to look at the probability of getting 3 heads in a row, when I get a head on the first one, the second coin still has a 1 in 2 chance of being a head. All right, so the first coin being a head did not affect the second coin, and the first and second don't affect the third. So I could get 3 heads in a row, and each one would have each event of getting a head would be a 1 in 2 probability, or a 50% if you like. So those are independent of each other, all right? So we can handle those probabilities very differently because the first event doesn't affect the second, which doesn't affect the third. In fact, you can see the logic of this. If I said, what is the probability of getting 5 heads in a row? It's unlikely, but it could happen, all right? Each time there's a 1 in 2 chance of getting a head. We're going to explore what that probability is. There is a probability that that could happen. If, on the other hand, I said with my deck of cards, what is the probability that I will get 5 queens in a row? We know the answer is 0, because by the time we get down to maybe we did get 4 queens in a row, not very likely, but we could. And then you all would know that the next card couldn't be a queen. So it would be a 0 in, I guess we've already taken 4 cards away. So there would be 48 cards. Let's see, if we took 4 away, yeah, there'd be 48 cards left. So we'd have a 0 in 48 chance of getting a queen on the last card. So the probability of getting 5 queens goes to 0, whereas the probability of getting 5 heads is not 0. So let's explore that question a little bit further. Okay, so first of all, I have our formula from the other day. If we want 2 things to happen, we should consider that, and both of them are going to happen. So let's for our cases that we've been looking at, let's just look at a simplified case where E is a head. I'm sorry, let's do drawing a queen on first card, and F is a queen on the second card. Just real quickly, the probability of E and F, those 2 things intersecting, would be the probability of a queen on the first card, which we established was 4 in 52, times the probability of a queen on the second card, which is 3 in 51, okay? And notice the E given F part matters because E has already happened. That's where we get down to only having 51 cards left and only having 3 queens left. So given that E happened, that we did draw a queen, we have to, that affects the probability for the second one. But if we turn this around and say E is a heads on first toss, and F is a heads on the second toss, we know that the probability of E intersecting F, we have a 1 in 2 chance, but it's kind of like replacing the queen back in the deck. We still have a 1 in 2 chance on the second toss. So we can just multiply those together. The probability of F given E is unaffected. And so we're able to say that this is just the probability of E times the probability of F. These are independent events. So today we'll only be focusing on independent events so we can multiply probabilities when we're looking for multiple things to happen. And we'll also see that when we need to add, when we have a union of events, there won't be any overlap in regions, so we can simply add up the union of events. Okay, so continuing along. The question that we started with is, what is the chance, or better yet, what is the probability of tossing 5 heads in a row? Okay, so we're just expanding on what we have right up here. We know that the probability, now we just have a string of events. We would have a bunch of letters that we could use. The probability of this happening, so we'll say the probability of 5H out of 5 tosses would be 1/2 times 1/2 times 1/2 times 1/2 times 1/2, which is better to write as 1/2 to the 5th, which is 1 out of 32. Okay, 2 to the 5th is 32. So there is a chance that you would in fact get 5 heads in a row. It's not a great chance. This is approximately 3%. If it was 1 out of 33.333 going on forever, it would be 3%. So that's very close to a 3% chance of happening. All right, so you wouldn't be absolutely shocked if it did happen. Be surprising, but not absolutely shocking for it to happen. All right. Now we want to go a little bit further with this and explore a series of questions, okay, that get a little more sophisticated as we go. Okay, what is the probability of, I'm just going to shorten this, 3H, then, that's the key word, 2 tails, 2T, I'll shorten that. Okay, so what is the probability of 3 heads and then 2 tails? Right? It turns out it should be the same. So we're going to have 3H, comma, I'll say 2 tails. The order matters, okay? So we're going to do, I probably should put the word then in here, because what is the probability of getting a heads on the first toss? It's 1 in 2. On the second toss, it's 1 in 2. And on the third toss, it's 1 in 2. Those are my probabilities for getting heads. And then what are the probabilities of getting tails? On the fourth toss, it would be 1 in 2. And in the fifth toss, it would be 1 in 2 of getting tails. And so you can see that we're back to 1/2 to the 5th power, or 1 in 32 chance. Now here, the order is specified. We have to get a heads, a heads, a heads, and then a tail and a tail. So it's no more likely than getting 5 heads in a row. All right. Now this is a much more interesting question. I'm going to shorten it just a little bit. Probability of 3 heads out of 5 tosses. Okay, so now we will get 3 heads and 3 tails, but we can do it in any combination. All right, so what we have is H, 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 tails, tails, but we can have any combination thereof. Okay, so we know from combinations we could look at C of 5 tosses, and we've selected 3 of the objects to be heads. Okay, you remember the notation could also be written that way, but the important thing is that the combinations are 5 factorial. If we have 3 of them selected, be 3 factorial over 2 factorial. The way I like to think about this is if the heads and tails were distinguished from each other, there'd be 5 factorial ways of getting them. If there was an H, let's say we put little subscripts, a 1, 2, and a 3, and a 1 and a 2. If those were distinct heads and tails, there'd be 5 factorial ways to order them. But if we get rid of the subscript, we have to divide out the 6 different ways that those heads could be arranged and the 2 different ways that the tails could be arranged, and divide those out of the distinct possibilities, and hence the combination works nicely. So that would be the number of ways we could get 3 heads out of 5 tosses, but we want the probability of that happening. So all we need to do is take the probability of getting 3 heads, then 2 tails, and then multiplying that by the number of ways it could happen. Okay, so there was 1 in 32 chance of getting 3 heads, then 5 tails. But if I look at 5, the combination of 5 taken 3 at a time, that would be 5 factorial over 3 factorial, 2 factorial. This is a good one to do by hand. That's 5 times 4 times 3 factorial over 3 factorial, 2 factorial. I'll write that out as 2 times 1. The 3's cancel, the 2 reduces to a 2, and so there are 10 ways that could happen. All right, so what happens here? The probability of 3H then, whoops, not then 2 tails. Let me just write, that's 3 heads out of 5 is going to be 10 times 1/32. Okay, so the order no longer matters. So there are 10 ways to make it happen. So that's 10 out of 32 or 5 out of 16. So a much more likely chance of getting 3 heads and then 3 heads out of the 5. All right. Now the probability would be the same for 2 heads, because if we get 2 heads, that means we had 3 tails, and the probability of getting 3 tails would be the same as it is for 3 heads. Okay, so we want to explore one final question here. This is slightly more sophisticated. The probability of getting 3 or more heads out of 5 tosses. Okay, keyword here is or. That is an or, OR. So the word or reminds us that we're looking at a union of events, okay? But when we look at this union of events, the events that we would be looking at is, event E would be getting exactly 3 heads. Event F could be getting 4 heads. That qualifies as 3 or more. And let's call it event G is getting 5 heads. If we were to draw out a Venn diagram, E, F, and G don't overlap at all. So if you remember the probability of E union F, that's just for 2 events, was the probability of E happening minus plus the probability of F happening minus the probability of E intersecting F. Well, the intersection isn't there. So we can just add these up, and in this case, we can add on plus the probability, since we're doing union G, we can add on plus the probability of G happening, all right? So there are no overlaps, so we can simply add those probabilities up. All right, so we have 3 different probabilities to figure out, okay? So the first probability would be looking at, so this would be event E, And we've already figured that out. There are 10 combinations. The probability of E is there were 10 combinations, each of which had a 1 in 32 chance of happening. So there was a 1 in 32 chance of getting heads, 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 tails, tails, but there are 10 ways to order that. If we were to look at event F, that would be heads, 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 tails, which would, again, if we required it to be in that order, the probability would be 1 in 32. But the probability of F happening, there are 5 different ways to arrange this. We could see that this is actually C5 taken 4 at a time times 1/32. You can put that in your calculator if you wish, or try to do it by hand. Actually, it's quicker to do that one by hand. And you'll see there are 5 ways you could do that. You can also think about it. How many places could the T be in? There are 5 different places to put the T. So 5 ways that that could happen. So 5 out of 32. So it might be nice to actually keep all of the denominators as a 32 so that we don't have to, we can compare these probabilities, and we're going to want to add them up. So keeping the denominator as a 32 is very nice. And then for G, it's possible that we could get all heads. Well, that was the first question. What's the probability of G happening? That's just 1 in 32. It's actually C5 taken 5 at a time times the probability, 1/32. Well, if you have 5 things that are all the same, there's only one way to order them. So we end up with 1 times 1/32. So that's 1/32. All right, so the probability of any one of those things happening is just the sum of all of the probabilities. Okay, so if we add those up, it was nice to keep them in terms of 30 seconds. We have 16 30-seconds, which you can see reduces to exactly 1/2. All right, so we have a exactly 1 in 2 probability of getting 3 or more heads out of 5 tosses. Okay, so we'll end this video here.